Hello, my name is Bill Robbins. This video that you're about to view is a review of basic semiconductor physics, about at the same level as an undergraduate course in semiconductor devices, usually in the third year. The purpose of this review is to provide a basis for a somewhat semi-quantitative discussion of several power electronic devices that are commonly used in switch mode power electronics. In this talk I'm going to cover four topics: conduction processes in semiconductors, description of what a p-n junction is, both in thermal equilibrium and with applied voltages, leading to the charge control model of a p-n junction and the exponential IV characteristic that we're familiar with, and finally a brief discussion of avalanche breakdown. When we talk about current flow in a semiconductor, the picture here on the right more or less summarizes what the important factors are. We assume we have a density of free electrons in this cylindrical volume of density n, and it's moving with a velocity v. Over on the left hand side is a derivation of the current density involving these parameters. I won't go through it, but the net result is the current density J is equal to the number of charge carriers per unit volume times the charge on each one times the velocity with which they're moving. In metals such as gold and platinum, aluminum, and other metals, the number density is very large, on the order of 10 to the 19th to 10 to the 23rd per cubic centimeter, and the conductivities are correspondingly high, 10 to the 7th ohms per meter. Insulators, on the other hand, like silicon dioxide, silicon nitride, and others, have very low free carrier densities. I've arbitrarily picked a dividing line of 10 to the 3rd per cubic centimeter. Low and high resistivity materials, such as silicon dioxide, the number is often less than 1 free carrier per unit volume, and the corresponding conductivities are very small. Semiconductors, such as silicon, gallium arsenide, and other materials, are intermediate between these two extremes. They can have carrier densities on the low side of 10 to the 8th to as large as 10 to the 19th, depending on the type of material and on the doping densities, and thus a very wide range of conductivities. The first question that comes to mind is, where do these free carriers come from, particularly in semiconductors? The next slide shows a somewhat schematic diagram of the silicon lattice. These circles that are shaded represent silicon atoms which are fixed in the crystalline lattice. The lines joining them to their nearest neighbors represent the covalent bonds. In each bond is one electron. Silicon has 4 electrons in its outer shell, which we call the valence electrons, which take part in this bonding. At absolute zero, all of the bonding sites are filled and there are no free electrons, and so the silicon is an insulator at absolute zero. However, at room temperature, each of these silicon atoms has some vibration energy due to thermal agitation. Some of the amplitudes of vibration are quite small, and a few are very, very large. Those that have sufficient energy and amplitudes of vibration stretch the covalent bond so much that the bond is broken, and the electron that normally occupies that bond is now free to roam through the crystal. Any silicon atom that has a broken covalent bond means that there is a positive charge residing on the silicon atom, because the screening charge, the electron that was in that bond site, or the valence bond site, is no longer screening it. There are a fairly large number of such silicon atoms that are ionized at any particular time. Even though percentage-wise it's a very small fraction of a 10 to the 23rd atoms per cubic centimeter. We need to consider this thermal ionization process in a little bit more detail, because just counting electrons is not sufficient. On this next slide I show a series of 3 separate times. At time t1, in this upper picture, I have a silicon atom that's been ionized and created an electron, free electron that I'm calling A. At a somewhat later time, a second electron, which I've labeled B, has been liberated from another covalent bond site and leaving a second silicon atom ionized. At time t3, the electron B has moved and been captured by the bond site from which electron A has come from. The net result of this transaction is, between times T1 to T3, is we have apparently created a free electron and a positive charge has moved in the opposite direction. So it's pretty clear from this simple description that when we are counting charge carriers, we have to count both the free electrons and the apparent movement of positive charge, which we call a hole. The number density of electrons in holes in this thermal ionization process is equal in number, so P is equal to N, and if the material is very pure, we call it intrinsic, and so P is equal to N is equal to the intrinsic carrier density N sub I. The intrinsic carrier density depends exponentially on temperature, and it's given by the formula that I've just highlighted. For silicon, Ni is about 10 to the 10th per cubic centimeter at room temperature, 300 degrees Kelvin. The parameters in the exponential relationship, T is the temperature in degrees Kelvin, K is Boltzmann's constant, and E is the energy gap, which is 1.1 electron volts for silicon. And finally, Q is the familiar 1.6 times 10 to the minus 19 coulombs. Now, if we could only deal with intrinsic semiconductors and were unable to change the number of holes and electrons at a particular temperature, the material would be far less useful than it really is. But we are able to change the number of free carriers even in thermal equilibrium by means of dopants. So we talk about putting impurities into the semiconductor, and when we do, we describe it as a doped semiconductor or an extrinsic semiconductor. In that situation, the number of holes, which is the thermal equilibrium number P0, is not equal to the number of free electrons, which we designate as N0 in thermal equilibrium, and neither N0 nor P0 are necessarily equal to Ni. So the question then comes, how do we estimate what the carrier densities are if we know the doping densities? There are two equations that describe this. The so-called law of mass action, which says that the product N0 times P0 is always equal to Ni squared, and secondly, charge neutrality. The total positive charge per unit volume must equal the total negative charge per unit volume. When we put in impurities, we contribute to the net positive or negative charge per unit volume. There are two types of impurities that we make use of. If we put in a so-called acceptor impurity, it comes in with free valence electrons. It needs a fourth electron in order to participate completely in the bonding in the silicon lattice. Inside of the environment of the silicon lattice, it's very easy for this acceptor impurity to capture a free electron and thus fill the fourth covalent bond. When this happens, it takes a free electron permanently out of the, at least on average, permanently out of the conduction process, and so we have a lot more free holes than we do free electrons. Solution of the two equations which I mentioned just above gives us the result that P0 is equal to N sub A and N0 is equal to Ni squared in a so-called p-type semiconductor. These are approximations in the limit that the doping density is much larger than Ni. The other kind of impurity that we can use is a so-called donor impurity. It comes in with 5 valence electrons. The fifth one is not needed for the covalent bonding, and it's very easy for it to be liberated from the donor atom at room temperature in the silicon lattice. And so it contributes an extra electron to the conduction process, and as a result we have a preponderance of free electrons and a much smaller number of free holes. And again, the densities, if we know the doping density, we can then calculate what the carrier densities are. Now, if you think about this process, the acceptor captures an extra electron, so it is now negatively charged. We say that the acceptor has been ionized and it's negatively charged. The donor impurity has given up an electron, so it is positively charged, but we talk about it being ionized as well. And so that is how we are able to say that the total negative charge on a per unit volume in the semiconductor is N0 plus the negatively charged ionized acceptors. The total positive charge is the thermal equilibrium number of holes plus the positively charged donor impurity. So far I have been describing the semiconductor in thermal equilibrium, where the generation rate of free carriers is balanced by mechanisms which cause them to disappear or recombine. And we have a steady state situation where N is equal to N naught and P is equal to P naught. However, when we apply currents and voltages to the semiconductor, we're in a non-equilibrium situation, and it may be that the total number of free electrons is larger than N naught and the total number of holes is larger than P naught. There are several mechanisms that can generate these excess carriers so that P is greater than P naught and N is greater than N naught. A couple of them are illuminating the semiconductor with light of appropriate wavelength that will break covalent bonds. That's the so-called photoelectric effect. A second mechanism is injection across the p-n junction. And finally, impact ionization. These latter two I'll be talking about a little bit later. But with these mechanisms active, we have excess holes and excess electrons. And the mechanisms that I have been talking about will create these excess carriers in equal numbers by the breaking of the covalent bonds. So we can write, as I've done up here, N is equal to N naught plus delta N, and P is equal to P naught. Excuse me for not having the proper notation here, plus delta N. If we do have excess carriers and we have a steady state generation rate, it will ultimately limit itself, and so we will have excess carrier densities that become constant independent of time because they'll be balanced by recombination. If we then turn off the generation rate, say as t is equal to 0, we're going to have a faster recombination rate than a generation rate, and the excess carriers will disappear. We describe that by a very simple rate equation which says d delta n by dt is equal to the negative of the excess carrier density divided by a constant tau. And the solution to that is an exponential decay. And tau is the so-called excess carrier lifetime, or shortened for carrier lifetime. This is a very important quantity in some of our semiconductor devices that we use in power electronics, and we'll have to consider the carrier lifetime in a little bit more detail in the next slide. Usually, in most situations, we consider the carrier lifetime to be constant and independent of changes in parameters in the silicon lattice. But there are two situations where the carrier lifetime does change that we have to consider. One is the carrier lifetime increases with temperature. Secondly, the carrier lifetime begins to decrease at large excess carrier densities. I show here an empirical formula on how the excess carrier lifetime depends on excess carrier density. The reason for the drop-off at carrier densities above this so-called background or level of N sub B is a mechanism called Auger recombination, which we don't have time to cover in this simple review. N sub B is on the order of 10 to the 16th to 10 to the 17th per cubic centimeter. The low-level lifetime tau naught is the carrier lifetime at low excess carrier densities on the order of 10 to the 15th or less. We need to control the carrier lifetime tau naught because in some of our devices there's a trade-off between how fast we can turn the device on and off and what its on-state losses are. If we design the device for very fast switching times, our on-state losses are going to be large. Or if we design the other way so that we have low on-state losses, the switching times are going to be unacceptably long. And so there's an optimum switching time, optimum carrier lifetime that achieves a reasonable balance between switching times and on-state losses. There are two general mechanisms we use to control the carrier lifetime at the time of fabrication of the device. We can use impurities such as gold, which are lifetime killers and act as recombination centers, or we can irradiate the device by high electron irradiation, which is more commonly used because it gives us better control over the carrier lifetime. The consequence of the electron irradiation is it creates imperfections in the crystalline lattice that act as recombination centers. Our next topic that we want to talk about is the flow of current in a semiconductor. There are two current flow mechanisms, drift and diffusion. Drift we're probably more familiar with. We apply a voltage externally across the p-n junction. That generates the electric field that's illustrated, pointing from left to right. That electric field pushes holes in the direction of the electric field, and it pushes the electrons in the opposite direction. The movement of these two charge carriers constitutes a current, density J, in the direction that I am illustrating here. Mathematically, we characterize the current density as the sum of two terms. The first term is the density of electrons times the mobility of the electrons times the electric field times the charge on each electron. The second term is the number of free holes plus the charge on each hole times the mobility of the holes times the electric field. The product of mobility times electric field is the velocity with which the carriers are moving. In silicon at room temperature, the mobility is about 1500 centimeters squared per volt second at doping densities under about 10 to the 15th per cubic centimeter. Similarly, the mobility for holes is about 500 centimeters squared per volt second, in the same range. If we go to higher doping densities, above 10 to the 15th, the mobilities begin to decrease. The other mechanism for current flow is by diffusion. If we have excess carrier densities, and I've illustrated here excess electrons as a function of position, we have a density gradient. And of course, the electrons are going to flow down the density gradient because of diffusion. Electrons flowing down the density gradient give us a contribution to the current, which I'm labeling J sub n, that moves off to the left. If we have free holes that have excess holes that have a density gradient, holes will diffuse down the density gradient, and that will constitute a current flow in the direction of the downward sloping density gradient. If we combine these two terms, the total current due to diffusion is due to the two terms. Diffusion of the electrons is characterized by the charge on each electron times the diffusion constant for the electrons times the density gradient dn dx. And then for the holes we have minus q times the hole diffusion constant times the density gradient dp dx. The reason for the minus sign here is usually the density gradient is considered positive when you're looking up the density gradient. There's a relationship that's very useful between the diffusion constant and the mobilities for the given carrier. The ratio of the diffusion constant over the mobility is equal to kT over Q, the so-called Einstein relationship. The total current density that's flowing in the semiconductor due to both drift and diffusion is summarized here. Usually in most device situations, one of the two mechanisms dominate. If you're near a p-n junction that's forward biased, the current flow is almost entirely by diffusion. If you're further away from the metallurgical junction, then the current flow is principally by drift. We now come to the second topic that I listed, and that is, what is a p-n junction and what are the details of its operation? A p-n junction is nothing more than the interface between a region of p-type material and a region of n-type material. We further distinguish a p-n junction by the nature of what the doping profile looks like. Here on the left I have a so-called abrupt junction or step junction where we have uniform doping in the p region until we reach the metallurgical junction, and then we have a step function change in the doping density to donors instead of acceptors. At the opposite extreme, here on the right, I have a linearly graded junction where the transition from p-type to n-type as you go through the metallurgical junction changes linearly. In all of the rest of our discussions, we're going to be assuming that we're dealing with step junctions, because in the semi-quantitative discussions that we're going to be getting into, there isn't much difference in the overall properties of the devices, whether you're using a step junction or a linearly graded junction. Once you have a step junction or a linearly graded junction, either way, you immediately form what is called a space charge region. Here's the metallurgical junction in the middle. Here on the N-type side, you have many more electrons immediately adjacent to the metallurgical junction than you do electrons on the P-type side immediately adjacent to the metallurgical junction. So naturally, electrons are going to tend to diffuse from the N-type side to the P-type side. Similarly, there are many more holes here on the P-type side adjacent to the metallurgical junction, and they're going to tend to diffuse to the N-type side where there are far fewer holes. Well, as that happens, we're going to uncover the ionized impurities. That is to say, we normally think in the bulk region here where they're far away from the p-n junction, the free carriers screen the ionized impurities, and so the net space charge is zero. But here, when we diffuse holes away from here to the right and to the N-type side, we uncover the ionized acceptor impurities, which have a negative charge. Similarly, we expose on the N-type side the positively charged donors. Well, as the diffusion process continues and we have more and more electrons diffusing to the left and holes to the right, we're building up space charge, positive on the right-hand side on the N-type side, negative on the P-type side. That generates the electric field that I'm talking about right here, which is in the direction such that it opposes the tendency of diffusion. This electric field is going to push electrons back toward the N-type side and holes back toward the P-type side. Very quickly, equilibrium is reached, even in thermal equilibrium, where the net number of carriers of each type crossing the metallurgical junction on average is zero. You will have a large number of electrons diffusing across into the P-type region, but you'll have an equal number being pushed back by the built-in electric field due to the formation of the space charge layer. And in that equilibrium situation, we're going to have a so-called space charge layer of width W. We need to look at this space charge layer in a little bit more detail because we need to describe it in a more quantitative fashion. We can do that by means of the following picture. Here in this first graph that I'm showing, I am plotting the space charge density as a function of position in the immediate vicinity of the metallurgical junction. I am showing a uniform negative space charge on the P-type side and a spatially uniform positive space charge on the P-type side. And that space charge region extends for a distance x sub n on the N-type side minus x sub p on the P-type side. Within that region, I am assuming that there are no free carriers, that the space charge region is completely depleted of excess of any free carriers. In reality, the carrier densities look more like this, but it's more difficult to find out what this distribution is and handle the arithmetic than it is the so-called depletion approximation. And we're only interested in an approximate numerical estimate of what's going on, so we'll use this depletion approximation. We can write Poisson's equation, which says that the second derivative of the electrostatic potential is proportional to the negative of the space charge density divided by the dielectric constant of silicon. If we integrate once as a function of position, we can get the electric field. That electric field is plotted here, and it is equal to a spatially linearly varying function of position outside of the depletion region at x greater than x sub n or x less than x sub p. The field is assumed to be zero because we have a very large number of free carriers. The electric field has a maximum right at the metallurgical junction, and I've shown you the equations for the electric field in each of the two space charge regions. If we integrate once more, we can then get the variation of the electrostatic potential as a function of position. The difference in the potential between minus x sub p and plus x sub n is the so-called contact potential phi sub c. And here is the contact potential in terms of the variables of the problem that of the pictures we've been dealing with. You'll notice that I can't quantitatively yet estimate what phi sub c is. Even though I know the doping densities, I do not know what x sub n is. So we need some further information in order to do that. So what we do is the following. I can describe the contact potential in the following way and estimate what its magnitude is in the following way. In thermal equilibrium, the total electron current density has to be zero. It's composed of a drift term and a diffusion term. If I take that equation and separate the variables, on the left-hand side, I have just the contact potential as a function of position. On the right-hand side, I have 1 over the density of the free carriers as a function of position. If I integrate across the depletion region, I can then come up with an expression for the contact potential. Phi at x sub n minus phi at minus x sub p, the minus sign here is missing in the x sub p, defines the contact potential, and it's equal to kT over q times the log of Na Nd over Ni squared. An example of the numerical value is shown here for silicon at room temperature with doping densities of 10 to the 16th. And this quantity right here is phi sub c, not f sub c. We can blame that on Microsoft Office not carrying through the intended lettering that I wanted. Once you know the contact potential, we can then estimate some of these other quantities. Let's go to reverse bias p-n junction, because we're not going to be using a p-n junction always at thermal equilibrium, because that doesn't have much of a practical application. By reverse bias, I mean I apply an external voltage, I make the n-type region positive with respect to the p-type, and current will flow, if any current flows at all, from the n-type region around through the device to the p-type side and then through the external circuit. The electric field due to the applied voltage is going to be in the same direction as the built-in electric field, which means I am going to be increasing the potential, the electrostatic potential that exists across the p-n junction. Here is the electrostatic potential, phi sub c difference, between the n-type and p-type side in thermal equilibrium, and here is the electrostatic potential V plus phi sub c when I apply the negative voltage. The other thing that we note is W naught, illustrated here, is the width of the space charge region at thermal equilibrium, whereas W of V is the width of the space charge region at the applied voltage V in the reverse direction. In order to support that external field, we have to have, inside the semiconductor, we have to have more space charge, and that's the reason for the increase in the width, because we have uniform space charge density, and the only way we get more space charge is to widen the depletion regions. Well, if I write that W at a voltage V is equal to x sub n plus x sub p, and I assume that they're now functions of voltage, and secondly, take the equation for phi sub c that I had before and simply add to that the voltage, I now assume that the x sub p in this equation and the x sub n in this equation are now functions of voltage. And then finally, I use charge neutrality, which says that the total positive charge on the n-type side depletion region is equal to the total negative charge on the negatively charged space charge region on the p-type side. If I solve these equations simultaneously, we find that the depletion layer is given by the expression I've just highlighted. Depends on the square root of the applied voltage divided by the contact potential. W naught is given by this equation, And finally, the maximum electric field is given down here. This maximum electric field is obviously going to increase as we increase the reverse bias voltage, and this is something we're going to have to consider when we describe impact ionization. We now have to consider the p-n junction under forward bias conditions. The slide I'm showing here shows a simple p-n junction where the applied voltage is positive on the p-type side and negative on the n-type side. The result of this is the electric field in the depletion region is now smaller because the electric field which is due to the applied voltage is in opposition to the built-in electric field. The consequence of that is the depletion region is now narrower because we need a fewer total amount of space charge. So the width of the depletion region at thermal equilibrium is larger than that under forward bias conditions. The other consequence is that the potential barrier for diffusion is now much lower, and so it's much easier for the minority carriers, which are holes in the p-type region, to diffuse across from the p region where they're the majority, and similarly for electrons on the n-type side to diffuse into the p-type region. As a consequence of this, we now have a large number of excess minority carriers, electrons on the p-type side and holes on the p-type side. Holes on the n-type side and electrons on the p-type side. The actual spatial distribution of these excess carriers is shown here for electrons on the p-type side and for holes on the n-type side. The spatial dependence is an exponential decay as you move away from the edge of the depletion region into the depths of the drift region. The spatial decay constant is a so-called diffusion length. For electrons on the p-type side, L sub n, that length is given by the square root of the product, the diffusion constant for electrons times the excess carrier lifetime for electrons, and a similar expression for the holes on the p-type side. The shaded area that I am showing here is the total number of excess electrons on the p-type side, and the shaded area here is the excess carriers on the n-type side. We can integrate the expressions that I have for the holes on the n-type side and electrons from the n-type side, and that's what I've shown down here. The result of that integration is this is the expression for the so-called total stored charge of electrons on the p-type side and total excess minority carrier stored charge, which is the holes on the n-type side. Now, as long as we have a steady state DC current, these distributions will also remain constant as a function of position. The value of the excess carrier densities right at the edge of the depletion region is given for electrons by this formula and for holes by this formula. And the important thing to note is, both for electrons and holes, the values at the edge of the depletion region is proportional to e to the qv over kt. So we'll be using this information in a few minutes in order to estimate what the IV characteristic is of this p-n junction under the assumptions that have led to these particular equations. In order to maintain that excess carrier density, I know that the excess holes are subject to recombination. To maintain a steady state distribution, I have to constantly bring in more holes on the p-type side and more on the n-type side and more electrons on the n-type side. So bringing in those electrons and holes means I have to have a current flow. The average current flow due to electrons that are on the p-type side is Q sub n over tau sub n, and the average current due to the excess holes on the n-type side is Q sub p over tau sub p. So, in the steady state, these two current terms are going to be the total current flow that's necessary to maintain those steady state distributions. Using the results from the previous slide, it's easy to show that the current density is given by this bracketed factor, e to the qv over kt minus 1, and then this large set of constants over here, which we identify as the so-called saturation current or reverse saturation current, J sub s. And here is J sub s written explicitly in terms of those variables. If I plot this current density as a function of applied voltage here on the far right, I get a graph that for positive voltages I have a current that's increasing very, very rapidly because of the exponential dependence of current on voltage. In the reverse direction, it appears as though I have zero current. So it looks as though I have a unipolar IV characteristic, meaning in the forward direction current flows quite easily, but in the reverse direction I have vanishingly small currents. If I break out the two curves separately, here is forward bias on the same scale as the original graph, showing the exponential growth of current with forward voltage. If I reverse bias the device, I have to change the vertical axis and make it much smaller per unit in order to display the small current that flows. Within a few tenths of a volt negative bias, I achieve a constant negative current, which we call minus J sub s, the reverse saturation current. When I plot the reverse saturation current on the same scale as the forward current, it appears as though I have zero current flow in the reverse direction. The reason for the constant current in the reverse direction, independent of the applied voltage, is fairly easy to see. Here is a picture again of the reverse biased device. On the n-type side, the hole density distribution goes from being equal to the thermal equilibrium number of holes far away from the metallurgical junction on the depletion layer down to zero at the edge of the depletion region. This curve is independent of the applied voltage. Similarly, the electron density on the p-type side goes from its thermal equilibrium value far away from the metallurgical junction down to zero at the depletion layer boundary, and it also is independent of the applied voltage. So with a constant gradient or distribution versus position, we have then a constant current flow. Finally, we need to go back and take notice of the fact that if we do reverse bias the p-n junction with a substantial voltage, I'm going to get a pretty large electric field there at the metallurgical junction, and this can have some severe consequences. What I'm showing here in this diagram is a couple of events where an initial electron comes in with a certain velocity and hits the silicon atom. If I assume that that electron has a large kinetic energy, when it hits the initial silicon atom, it may cause the silicon atom to have such an amplitude of vibration that it breaks one of the covalent bonds, and that means a free electron is liberated. So as a consequence of that high energy electron hitting the silicon atom after the collision, I have two free electrons, the initial one plus the one from the broken bond. Within a very short time, those two electrons are going to acquire energy from the applied electric field, and if they also undergo collisions with a silicon lattice that break covalent bonds, then after these two scattering events, I started with one free electron, I wind up with four. Now the mean time between collisions is on the order of 10 to the minus 12 to 10 to the minus 14 seconds. So very, very quickly, I can build up a very large number of excess carriers due to what is called impact ionization. It's a chain reaction-like event. It occurs very, very quickly. If this occurs, it has some disastrous consequences if you don't terminate it very quickly, because you're now going to have a large number of excess carriers, which then means large current flow in the presence of very high voltage. And that power dissipation that results from that can easily destroy the device if you don't terminate impact ionization very quickly, or better yet, completely avoid it. An approximate estimate of what electric field is required can be obtained from the following consideration. We know that the kinetic energy is 1/2 mv squared. If that is equal to the energy required to break a covalent bond, and we can relate that energy to the electric field, then we can solve for the electric field. Well, the velocity that the electron acquires in the time t sub c between collisions is given by Q times the breakdown field strength times the average time between collisions divided by the mass. So setting the kinetic energy equal, in this case, to the energy required to break a covalent bond, which is in joules equal to Q times the energy gap, and solving for the value of the electric field required to do that, we obtain this expression. If I evaluate this numerically for silicon, using the quantities that I'm showing down here, I would roughly estimate for silicon about 400,000 volts per centimeter is the breakdown field strength. Experimentally, it's on the order of about 2 to 3 times 10 to the 5th volts per centimeter. This sounds like a fairly accurate estimate, but I've rigged the books a little bit, so to speak, in that I've chosen sort of an average collision time that gives us this breakdown field strength. To actually get a reasonable estimate from a theoretical viewpoint, one needs to take into account the fact that there's a very large number of electrons that are free and acquiring energy from the electric field, and this large number of electrons has a wide distribution in the energies, and only a small fraction of them are going to acquire sufficient energy between collisions. So there's a fairly complicated averaging process that must be done. But nonetheless, when you do that, you come up with theoretical estimates on the order of what I've shown here. And so we can end this discussion by reminding you again what I've said. When you reverse bias the p-n junction, you must take note of what the breakdown field strength is and how that is related to the maximum voltage that you can apply in reverse bias. So at this point, I'm going to conclude the discussion of the semiconductor review.